First of all, hi everyone, and thank you for staying behind. I know you've had lunch, and so I'm guessing a couple of people are slowly starting to get a bit tired, so thank you for staying behind. And also thank you to the organizers also for inviting me for this session. So my name is Chiedu, as has been said, and I work with AWS, and I work there as a senior solutions architect. And today I'm going to be talking about a topic I've titled Shaving Milliseconds. Okay, so quick show of hands. Has anyone had this before on your browser screen? Okay, so I think that's pretty much everyone, right? So you're trying to get to a checkout button, you're trying to click a reservation button, you're trying to do something on a website, and then this pops up, right? And because this is a tech conference, we are sort of owners from the point of view of the fact that lots of us manage these applications behind the scene. And so either we're getting a ticket or a case or a support being raised to say, look, your application is slow, you need to go fix it, you need to make it faster. The executive is trying to log into a dashboard or do something, right? And so basically what this talk is about is how exactly can you optimize your applications for speed. So if you're getting your page loading in 5 seconds, for instance, can you get it down to 4 seconds? If it's 1 millisecond, can you get it down to 0.5 potentially, right? And all of this is in the context of AWS, but that doesn't mean that you cannot use the same architecture patterns and references for the cloud providers as well. So this is just basically 2 stats here that has been researched upon. So one from Amazon, us, and another from Deloitte, that basically shows the correlation between load time on a website and how that basically affects business revenues and conversion rates, right? So effectively, for every 100 milliseconds time that it takes for your page to load, we discovered that that actually leads to a decrease in 1% of revenue increase if you flip it around. Now, in terms of the way I sort of designed this presentation, I'm going to use a storytelling technique that in networking is called a day in the life of a packet. And the way it works is, imagine your user's traffic leaving their device, trying to get to your application. What are all the hops that it goes through? And for each of those hops, what can you actually do to actually optimize the speed along the path? So let's start. Now you have your users somewhere out there on the internet. They log onto their mobile device, their iPad, computer, whatever it is they are using, Oculus Rift maybe. And they're trying to basically make access or make a connection to your application to download a meme, an emoji, or do something on your application. Typically, this is how the traffic goes over the internet, right? So the traffic goes from their device through the ISP to the internet, and then from there it goes to the AWS Edge, which is basically where we connect with upstream providers. We receive that traffic, and then we basically switch it through our fiber backbone, and then eventually we deliver that packet or that piece of information to your application. Now, what we have over here is basically a visual representation of the current AWS fiber infrastructure as it stands. And you can pretty much see that we connect pretty much most areas in the world in terms of infrastructure and connection. Two just, I guess, key things about this connection. So these are basically redundant 100 gigabits Ethernet fiber connections that go across the internet. And for every dot you can see there, that's basically a place where we have a point of presence. So this could be a region, which I'll explain very soon. It could be a CloudFront point of presence, which is our content delivery network. Or it could be other devices or infrastructure that we've actually placed in that particular location. Now, your user's traffic has left from their device and is trying to get out into the internet. And you're the one in charge of building that application, maintaining the code base. What can you do to actually optimize the speed? The first thing to say here is that there's actually not a lot you can do. And the reason for that, which would be almost fairly obvious, is that the traffic from the clients to the ISP is not really within your control, right? So they're making use of their ISP. It could be Optus or Telstra or whoever that is, right? You don't really manage that sort of connection from the user to the ISP. However, there's something that you can do. Now, if you're building an application, first of all, for many of us, you might be building copies of that application in a single location. So in AWS, a region is basically a geographic location where you keep your application. So this could be your database, your compute, your serverless, whatever that could be, right? Now, the key piece of advice to take away from this slide is that as much as possible, you should ensure that your application stays close enough to your users. So you probably have heard this very often, but you can't go faster than the speed of light, at least for now, right? Maybe there's going to be like some technological breakthrough sometime in the future. But for now, distance imposes speed constraints, right, in terms of how much packets we can actually push and how much your packets can be switched through the fiber core. So based off of that, what you want to do is to ensure that your users' traffic are kept as close as possible to the actual application. And so that way it doesn't have to route through multiple continents and land and sea and everything until it eventually gets to your application, right? Now, for some of you here, you might, for regulatory reasons or for content reasons or other reasons, have multiple copies in multiple regions. But you still want to ensure that the latency is also down. What can you do? In AWS for Route 53, which is our DNS-based service, we have what's known as the latency policy. And so if you were to configure this effectively, what that means is that we have a look at the source IP of the client coming in, and we can tell what country they're coming in from and where exactly they're trying to go, and we can measure the latency between there. And so if you have a traffic, for instance, coming from, say, Sydney region, for instance, and you have an application both in Sydney and Melbourne, we can tell where the client's IP's traffic originated from and say you need to route this traffic and keep it within Sydney. So don't send it to the Melbourne application because that's just going to be higher latency. So that's something to think about. Now, the traffic moves from the internet, right? So now, hooray, it's left the ISP and it's trying to get into the AWS backbone. How can you optimize for speed at this layer? There's a couple of things you can do here. The first is you can make use of a service called Amazon CloudFront, which is our content delivery network. And the way this works is that it basically keeps content close to a lot of the edge locations that we maintain all over the world. And that's one way of that CloudFront works. The other thing it does is that it actually keeps the content that users frequently access close to the edge. And so if you think about it, a lot of times it's the same images, it's the same JavaScript, it's the same .css files, it's the same content that users are actually trying to retrieve from your application, right? So with CloudFront, most of that content is kept close to the edge, and the user's traffic doesn't have to go all the way to the origin to go pick up the traffic. The other service I've mentioned here that I don't think a lot of people actually are cognizant about is a service called Global Accelerator. And we launched this, I think, about 4 years ago or so. And it's very similar to CloudFront, but the difference is that it's not just web traffic, it's also any type of layer 4 traffic. So think UDP traffic, voice traffic, gaming traffic, any type of traffic basically that rides on layer 4. And I won't bore you with the details, but the trick of what we do is we use a technology called Anycast, and I'm going to explain it a little bit on the next slide. But what we do is we publish all our IP addresses across the globe, and so that way traffic gets into the AWS backbone a lot faster, but I'll explain it in the next slide. The third thing you can do is consider a service known as AWS Outpost, and this is basically AWS infrastructure sitting in your data center. So we basically have 1U form factor, 2U form factor, and a whole 42U full rack that basically has the AWS services. So think EC2, load balancers, and the rest, but actually running in your own data center. And we have a couple of customers that use this if they need to keep traffic, both for latency reasons and for data residency reasons. And finally is a service or a feature called AWS Local Zones. And this is actually available in Perth. I've actually worked with a customer of ours that used this for their voice-based systems. And what this is effectively is if you're building applications for your users that are majority in Perth, and you don't want to keep it in our Sydney region or Melbourne region, we actually have a service where you can actually keep the content close to the Perth users and region known as local zone. So think of it effectively as a smaller type of region, but it has most of the major services that you typically use, so like EC2 and RDS. Okay, so I'm just going to quickly talk about Global Accelerator because I mentioned it in the previous slide. What's Global Accelerator? Now, For those of you that might have done anything in networking, you know that that first diagram is a bit of a nightmare, right? So you're doing a trace route and you're having to look at all the hops that the packet is going through, and you're like, oh, it's leaving and it's going to the first ISP and the second ISP and the third ISP and the fourth and fifth and sixth and on before the traffic actually gets to your data center, right? What Global Accelerator does is it removes all of the hops and all the multiple networks that the user has to traverse before it gets into the AWS region. And it does this basically by publishing the IPs close enough to the users. So rather than the user having to switch their traffic all the way through across the globe and multiple fiber connection, we get this traffic close enough to the edge and close enough to where the user's traffic originates from. And that's the trick. And I can go into more details if I have more time, but probably maybe another day or session. And this is a test that I ran, I think, 2 days ago or so. And feel free to check out the tool on the right-hand side and test what you can also see as well. But this is basically what you have if you are to test direct users access or traffic going to the internet. And then what if you were to put Global Accelerator in front of that particular ELB or EC2 or whatever service that you actually have. And so what you can see over here is that if you were to use Global Accelerator, you would have 81% faster speed and latency for Sydney region and 37%. Now, obviously, these figures fluctuate, but this is sort of the mean of what I was able to pull out, right? Now, the traffic has left the edge, which is where we pair with our upstream providers, and it's gotten into the AWS backbone. How do you ensure that that path is also optimized for, right? Now, this is something, again, also those of you that are very familiar with networking probably have heard about or spoken about before. And it's something in networking known as jumbo frames. The way to think about jumbo frames is when your device is sending traffic, it typically doesn't push everything all at once. So you have a 5 megabytes email, you have a 20 megabytes photo to share or something to do. Your network interface card is going to chunk all of that packet into smaller bits, right? Because it can't send all of it all at once. Now, the typical size of a packet that's leaving your network interface card is 1,500 bytes. That's sort of the general thing we've all agreed upon as a safe value so as not to start to fragment or push the limits. And anything more than this, generally speaking, the application or the network interface card has to basically cut that data into multiple chunks until it gets to the final one, and it sends it through to the internet, and then the other endpoints reassembles it. Now, for traffic within the AWS VPC, it's possible to make use of what's known as jumbo frames. And what this is effectively is increasing the amount of data that you can actually put into a single packet. And so typically, a single packet is carrying 1,500 bytes. You can actually increase it to 9,000 bytes with jumbo frames. And so what that means is that you have less overhead in terms of the IP traffic, and then less wastage as well. Now, we've gotten to the VPC, right? Is there anything that we can actually do to optimize for the speed when the packet gets into the VPC and is about to get to our resources? The answer is yes. So I've put together a couple of techniques also as well to consider. Now, some of you might be developers here, and this is something that you can either share with the other infrastructure folks you work with, or if you maintain the application yourself, you definitely want to consider it as well. Now, the first one I put here is consider keeping VPC traffic intra-AZ. And I use the word consider because everything in architecture is about trade-off, right? So there could be a trade-off here between this and availability. So if you have, 12 nines, for instance, that the CTO or CIO says you need to maintain, then we can have a conversation in terms of how can you do that in tandem with this. But if you're running an application where that's not really a problem and you can't keep traffic within the same AZ, then that's the first thing to consider. So if we think back to what I said previously, a region is a location where we have servers to host your applications. Within the region, we carve out spaces known as availability zone. And so that's where you basically isolate the application such that anything happening here does not affect the other one, right? But what can also happen is if you have an application in one AZ, so you have a load balancer or you have an EC2 instance or a container or a function, and it wants to speak to another application in another AZ. Now that traffic obviously needs to get routed across kilometers of fiber, right? And generally speaking, that's low digits, single digit actually milliseconds. But however, if you're trying to push the extreme, you can keep the compute or the resources within the same AZ, and that's where also you're shaving off milliseconds. The second thing to consider is the right type of instance, and this is also very important because sometimes you're working with customers or you're working on issues and it's like, no, the bandwidth is slow or this is happening, and then you go and you check the logs and maybe it's like a T2 micro or one of the smallest instances, and it's not bad if it serves the purpose, right? However, again, profile the type of traffic that you're using. Is it a network intensive type of application or traffic? And if it is, have a look through the types of EC2 instances that we have and select the right instance for that particular profile, right? So general rule of thumb, the higher the amount of virtual CPUs in an instance, the higher the amount of bandwidth that we actually have allocated to that EC2 instance. The third thing to consider is something we call placement groups. And this is basically something that's similar to the technology, I guess, concept called clustering, where you're putting groups of related applications within the same racks or servers or virtual switching parts or network. And there are different types of placement groups, but the long and short of this is if you have applications also where low latency is a strong requirement, then you also want to consider making use of placement groups. And what this does is when the algorithm that we run behind the scene to place your EC2 instance gets initiated, we will try as much as possible to keep the instances in the same cluster of racks or servers or switches. So that way they don't have to talk very far apart from each other. The fourth one is a setting called enhanced networking. It's just basically a setting that you turn on. There's nothing much more to say about it. I don't really know quite much about the technical details, but it's something that is available on a lot of our EC2 instances that you can turn on and you can get faster latency on. The fifth one is consider using Amazon Elasticache. And this is basically a managed service for Redis and Memcached, which I would imagine many of you use. And it's basically an in-memory storage or database type service where if you have, again, similar to CloudFront, users accessing the same set of frequent database tables or rows or assets, you can put these in front of that particular RDS instance or database. And rather than your traffic going all the way and overloading your database instance and pushing the CPU and the speed on that as well, you have this traffic get into Elasticache. The other thing also is that it's an in-memory store, which means that it's optimized for speed. So if you know anything about in-memory, it's generally better than not in-memory. The last one I'm going to speak about in the next slide, but this is a feature that we've called Private Link, which has been around for a while. And if you're not making use of it today and your architecture supports it, I would definitely consider making use of it. Now, before we launched Private Link, if you look at this diagram, you can basically see that the EC2 instance in the consumer account is trying to connect to S3, for instance, right? So that's our storage, object storage service for files and the rest. There's also DynamoDB, IoT, SNS, and the rest on the left-hand side. Now, generally speaking, if you don't have Private Link, this traffic needs to route all the way through to our border network or even potentially to the internet. So in other words, each time you have an EC2 instance, you run AWS S3 commands to put something in the bucket or store a piece of file or do something else. That traffic will, generally speaking, have to go all the way through to the border and then come back. With Private Link, we actually deploy the resources within your VPC. And so that way, if you're making use of any AWS service, you basically get two advantages. The first is security. So when we speak with sort of our heavily regulated customers, FSI, healthcare, and the rest, they would almost definitely be making use of this service because for them it's like, no, everything needs to be private for the most part. And the other thing that you also get is also the speed. Because again, if you look at the packets that are leaving the EC2 instance here, it's basically routing within the VPC and not going all the way through to the border network. And finally, the traffic has gotten to your EC2 instance, to your Lambda serverless function, to your ECS or Kubernetes container. What can you do to optimize it from the point of view of network protocols and settings? Couple of things. The first is consider compression, right? So wherever possible, if you can compress content on the server, on CloudFront, on the ELB, or wherever it is, you're obviously going to get faster throughput and lower latency in terms of what you're delivering, right? Because if you have an image that's 1 megabyte and another one that's, say, 100 kilobytes, obviously 100 kilobytes is going to be faster in terms of delivering back to your clients. So consider compression as a technology to use where possible. The second is have a look at the suite of TLS encryption ciphers and protocols that you have, and where possible, turn on version 1.3. It's not just only a security thing, because obviously as standards evolve, we optimize for the ciphers, elliptic curve, RSA, and all of that. But also the amount of handshake that takes place when you make use of TLS version 1.3 is also reduced. So if you look at the diagram on the right-hand side, on the left, you can see the amount of round trip it takes for a client and a server to establish connection to have TLS version 1.2 connection. And this is your typical, you're trying to go to pick your favorite internet on the website, right? It's all TLS for sure. Now, if the website is using version 1.2, it's going to go through all of that handshake that you see there on the left-hand side. If you're making use of version 1.3, it cuts that down to a single round trip time. And it also has a very interesting feature known as session resumption, where even when the traffic becomes idle, if the client comes back in again, because it had stored certain states of the cipher details, it can resume the connection. The next thing to consider as much as possible is turning on HTTP version 2. And when I say turning on here, at least I can speak for AWS, for the most part, this is usually just settings. So you can go to your CloudFront, you can go to your load balancer, and just literally turn on a setting. Consider turning on HTTP version 2. HTTP version 2 as a protocol has been built to be faster than version 1.1, which also has been built to be faster than 1.0. The fourth thing is consider WebSockets. Now, not all applications will support it, but if your application supports it, consider WebSockets, because it's basically a protocol that allows the server to also send traffic back to the clients. So if you think of web architecture, typically the server cannot send content to the client without the client requesting. So the client makes a get, it makes a put, it makes a post, and then the server says 200 OK. In WebSockets, the server can send traffic directly, and so that's where you save on the request from the clients that needs to be made. The fourth is a very important thing also I say a lot of customers do wrongly, is the timeout value. So every application has a timer, every load balancer, CloudFront, whatever it is, has a timer. What you want to ensure is that it's not too short, because if it's too short, then your client needs to always create a new connection, and all of that time basically adds to latency. And then finally, as much as possible, reduce the amount of DNS lookup, because obviously that then means that the client is making DNS lookup call to the domain servers, and similar also with HTTP redirect. So this brings me to the end of my talk. We've gone all the way through from when the client's packet leaves from the device, it goes to the ISP, into the internet, it goes to the AWS edge, it goes into the AWS backbone, and finally to the VPC. And basically those are some tips and architecture patterns and best practices to consider if you're trying to optimize for latency on the AWS infrastructure and services. Thank you. And finally, if I might add, if you're interested, feel free to fill out a survey and put in any comments you like. If you liked it, if you didn't, put in comments as well. Awesome.
Great, thank you. And just to note, that's not an official latency survey.
Yeah.
That's an internal AWS one. So please fill in both surveys. Chiedu. Great. Did we have any questions from the audience? Oof. Sam, making me walk all the way over there.
Just a tiny one. You mentioned HTTP2. If you have support for HTTP3, would that be advisable?
Okay, so if you have support for HTTP3, you mean on the AWS services?
Agnostic to AWS, wherever you're hosting.
Yeah. So in terms of the services we support right now, to be honest, I can't say for sure as to if we support HTTP version 3. But generally speaking, the way the protocols get built is that they get built for security and speed. And so with HTTP version 3, I would imagine that the speed is better than version 2, better than version 1.1. Where it gets more tricky is in terms of the interoperability. So what if your client doesn't actually sort of support it, right? And so you want to ensure that HTTP version 3 supports the ability to fall back to version 2 if the client doesn't support it. But definitely, I would recommend turning that on as well if like your servers or load balancers or content delivery network supports it. Yep.
Amazing, thank you.